Hello and welcome to this lecture. In this lecture, I would introduce you to how the kinetic modeling is done in Aspen Hysys. So now our learning objectives are the introduction to reaction kinetics modeling in Aspen Hysys, how to interpret and extract kinetic data from research sources, and then how to model kinetic reactions in Aspen Hysys. So this particular tutorial would cover all of these, right? So before we enter into the Aspen Hysys software, I like to do certain explanations and illustrations so that you can be on the same page while we are modeling in the software. So this particular introduction is like the most important part of this particular tutorial. So I urge you to actually follow through this introduction before you get to the point where we start the modeling. So I would like you to take note of this introduction. So first we are starting with the introduction to reaction kinetics. So for that we are making use of two basic reactions. We have the first reaction as A to give you B. Now, so A is your reactant and then your product is B. So you have a reaction where A reacts to produce B, right? And also you have a backward reaction. So this is more like a reversible process. So A reacts to give you B, and then some of B also reacts back to give you A, right? So that's the first reaction we are going to be exploring in this tutorial. Then the second one is where A plus B gives you C plus D, right? And it is also a reversible process, right? So C plus D also gives you A plus B, right? So now these reactions can actually be specified in terms of their rate expressions. So you can actually generate rate expressions for these reactions as regards their kinetics, right? So for example, if you want to generate a rate expression for this first reaction, you have R, which is the rate of the chemical reaction, is equal to Kf Am minus Kb Bn. And then for the second equation, the second reaction, you have R is equal to Kf Am Bn minus Kb Ci Dj, right? So basically it's just the multiplication of K times the concentration, the concentration of the reactant, right? So the rate expression is just a multiplication of the rate constant times the concentration of the reactant, right? So but in the case where we have Kf Am minus Kb Bn, the Kb caters for the reverse process, right? So you have this minus Kb Bn, right? So Kf is the rate constant of the forward reaction, while Kb is the rate constant of the reverse reaction, right? So this rate expression is actually for a reversible process as well as this one. So from here we have the definition of all the variables in the rate expression. So you have R is the rate of the chemical reaction, then you have Kf is the rate constant for the forward reaction, Kb is the rate constant of the backward reaction, then you have the I, J, M and N. They are the exponents of the different reactants, right? They are the exponents of the different reactants, Mn, Ij, right? Mn. Yeah, and they actually are used to determine the order of the reaction. Then you have the small a, small b, yes, and then the small c, small d. Those are the stoichiometric coefficients of the reactants and products respectively, right? So that is just the introduction, and this is the rate expression for these two reactions that we are going to be studying. Then moving on, we have the rate constant, which is K, right? So we have K for both the forward and the backward reactions. So K can be expressed as K is equal to A e raised to power minus EA over RT, right? Where A is the pre-exponential factor, then EA is the activation energy, R is the universal gas constant, and T stands for temperature, right? So these are some of these things are things you are already a bit familiar with, but I feel it's very important to actually restate some of them before we go into the modeling, right? So moving on, moving on. So now, Aspen softwares actually accept data, I mean kinetic data, in a configuration that is similar to what we have already stated based on the rate constant and then the rate expressions for the reactions that we have above, right? So Aspen Hysys accepts data in a way that is similar to what we have above, but then we need to properly understand how to actually input the kinetics data into the software, and that is where this introduction actually gets more interesting. So now it says Aspen softwares are configured to accept data in the forms expressed above. All that is required is to properly understand how to input such data. Aspen works based on a general rate expression below, which is similar to what we have above, right? So this rate expression, which is equation 4, is basically how Aspen actually works in terms of reaction kinetics and rate of chemical reactions. So you have R is equal to K into T raised to power N E raised to power minus E over RT. Then you have the product notation, right? And then you have Ci raised to power alpha times T raised to power B, right? So from here you have you have Ci, right? Ci raised to power alpha, and Ci raised to power alpha represents the concentration of each of the reactants involved in that particular reaction. So you have your product notation here. So what this product notation signifies is that you are going to be multiplying the concentration of all the individual reactants in that reaction, right? So that's why you have the product notation pi I to n, right? Pi I to n. That means you are multiplying the concentration of all the reactants involved in that particular reaction, right? So we have where R represents the rate of the reaction, then K is the pre-exponential factor, which is represented as A, in the rate constant expression in equation 3, right? Then you have E is the activation energy, then you have T is temperature, then R is the universal gas constant, and Ci is the concentration basis, right? Then you also have alpha. Alpha is the exponent of each of the reactants, right? So the reactant exponent, that is what you have as alpha, right? So this is the general equation that Aspen softwares actually work with. So moving on now, this equation 4 right here is actually for an irreversible process, right? An irreversible process. Now, for a reversible process, we'll be making use of equation 5, right? Equation 5 right here. Equation 5 just takes account of the backward reaction, right? So this the first part of it is for the forward reaction, while the second part is for the backward reaction. So you see you have K, and here you have K prime. So K is the same as Kf, which is the rate constant of the forward reaction, and then you have K prime, which is also Kb, and which is the rate constant of the backward reaction, right? So basically this is how all of this works, right? So now if we make an assumption that N here, and then B as well, right? So we have t raised to power n and t raised to power b. So if we make assumption that n and b are 0, as well as b prime, right? So if we make an assumption that n, b and b prime are 0, this equation 5 will reduce to equation 7, and then equation 4 would reduce to equation 6, right? So you have all of that. So you have t raised to power 0 will give you 1. Then you have t raised to power b, that is t raised to power 0 will still give you 1. And then you have t raised to power b prime 1, and then t raised to power n, that's t raised to power 0 will still give you 1. So it reduces from this right here to what we have here, and this now is actually similar to what we have initially, right? So now so if we now apply these equations, if we apply equation 7 to equation 1 and 2, right, which was the rate expression of the first the two reactions we are studying in this introduction. So we are applying equation 7, which is this, right, which is the reduced form. We are applying it to these rate expressions that we generated for those two reactions under study. You will get equation 8 and 9, right? So if you look at it closely, you have R is equal to kf a raised to power m minus kb b raised to power n. Now applying equation 7 will give you applying equation 7 will give you equation 8. So you have k e raised to power minus e over rt c raised to power a, which is the concentration of a, c a raised to power m, right? So which is the concentration of a, minus k prime e raised to power minus e over rt c raised to power n cb raised to power n, which is the concentration of b, right? So if you look at this and you apply this to equation 1, yes, this is equation 1, you will get equation 8. And also if you also apply equation 7 to this equation 2, you will also have equation 9, right? So as you can see, you are multiplying the concentrations of the reactants, right, for both the forward and the backward reactions, right? So you are multiplying the concentration of the reactants, and that is the essence of this part of the rate expression, the part where you have the product notation and then the concentration, right? So that's how these equations were derived, right? So then you now have this, right? So these equation 8 and 9 can otherwise be expressed as equations 10 and 11, right? Equations 10 and 11. So you have this, you also have it like this and like this, right? So the essence of showing you these two is so that you don't get confused, right? So because in as much as normally K is used to represent rate constant, right? That's what K stands for. In general terms, K represents rate constant, but in some cases, I have seen where K is used as the pre-exponential factor, right? I've seen cases where some people use K as the pre-exponential factor, but normally K is supposed to be the rate constant, right? So now, that is why I decided to actually bring up these two together. So in case you see your rate equation like this or like this, you will not get confused, right? Right? So you won't get confused, right? So basically it can either be like this or it can be like this, depending. So the next agenda now is to understand how to interpret kinetic data, right? So basically, kinetic data is generated via experimentation, right? So most of the time, if you are modeling a process and you actually want to incorporate kinetics into your model, then you most likely want to get your data from research, right? So you get your data from maybe research journals or papers, right? So now the issue is, how do you properly understand the data that you're actually getting from these papers, right? So that is the next agenda in this particular tutorial, right? So now, when extracting kinetic data from any source at all, it is important to take note of two things, right? There are two things that are actually very important that you must take note of. Number one is the rate unit, right? The rate unit, and then the concentration basis, right? The rate unit and then the concentration basis. These are two things that are very, very important, right? They are very, very important. So now, it says kinetics can be expressed in the following ways. Now, let's look at a rate equation, right? A rate equation that I imported to this document. So we have this. So we have we have this reaction. This one is an irreversible process. Yeah, irreversible process. So you have C3H6O to give you H2O plus, no, sorry, C3H6O plus H2O to give you C3H8O2, right? So it's an irreversible process. And then you have the rate expression as this, right? You have the rate expression as this. So for example, in a paper, you can actually see your rate expression from a research paper as something like this, right? And like I said, it's an irreversible process, so automatically you don't have a backward rate expression, right? So you just have the forward rate expression. There is no backward rate expression. There is no K prime, there is no KB in this particular rate expression, as you can see, right? So if you compare this rate expression with equation 11, right? If we compare it with equation 11, you will see that A prime is equal to 0, right? Because equation 11 is this minus this, right? And from here, we don't have any minus and we don't have any other expression afterward, right? So we just have the first expression, which represents the forward reaction, right? So automatically you will know that A prime is equal to 0, right? And if A prime is 0, every other thing that is attached to A prime would automatically be 0, right? Because 0 times whatever is here is already 0. So A prime is 0. Then you have A, which is the pre-exponential factor of the forward reaction, is 9.15 times 10 raised to the power 22. Then you have E, right? If you are comparing this with this, you have E is minus 1.556 times 10 raised to the power 8, right? Based on comparison. Then from here, you have CA is going to be C3H6O, right? And then M is going to be 2, right? So you see it, if you compare equation 11 and this rate expression, you see that M is equal to 2, right? And then CB is equal to CH2O, right? Because we have A plus B. So A is C3H6O while B is H2O, right? So you have CB as CH2O, and then we have CB, then we have N, which is the exponential. N will be 0, right? N is automatically 0 because the concentration of H2O is absent, as you can see, right? So the concentration of H2O is absent, so automatically H2ON will be 0, right? So N will be 0 for this particular one. So you see, this is how you can actually interpret some of the kinetic data that you actually find in your research sources, right? Now, another thing to take note of is that the rate constant, right? The rate constant can be expressed in the form below, right? So sometimes they may give you your rate constant in the lean form. So you have ln k is equal to a plus b over t plus c ln t plus dt, right? So, and you have that a, b, c, and d are constants, right? Now, in most cases, c and d are usually equal to 0. So if c and d is 0, the equation reduces to ln k is equal to a plus b over t, right? So you have ln k is equal to a plus b over t. Now, if you take exponential of both sides, you have this next expression, which is k is equal to e raised to power a times e raised to power b over t, right? Now, comparing this with the rate constant equation, which is equation 3, you will have that a is equal to e raised to power a, right? And b is equal to minus e over r, right? So as you are looking at all these expressions, you can actually pause and actually look at them properly to properly understand what I'm actually saying. So what I said is, you compare this expression here. If you can see my cursor, you compare this expression with equation 3, right? With equation 3, and you will have that b is equal to minus e over r, yes, minus e over r, and then a is equal to e raised to power a, right? Another form that this rate constant can be expressed is this, where you have ln k is equal to minus e a over rt plus ln a, right? So in this case, all you need to do is take exponential of both sides, and once you do that, you would actually get back to equation 3, right? So if you take exponential of both sides, you will get back to equation 3. So some of these things are the ways in which some of this data might be expressed in some of the research sources, right? So that is why I found it important to actually bring them into this particular tutorial, right? So the next thing now is to specify the relationship between k and k prime, right? So k is kf, which is the rate constant of the forward reaction, and k prime is kb, which is the rate constant of the backward reaction, right? So what is the relationship between these two? Now, the relationship between these two is big K, right? Big K or capital K, which signifies the equilibrium constant of the reaction, right? So equation 12 shows us the relationship between K and K prime. So you have K equilibrium, or big K or capital K, is equal to small k over small k prime, right? So this is the relationship between K and K prime, right? That is KF and KB, right? So that's it. Then what do we have next? Okay, so basically this is the environment where you specify kinetic reactions, right? You can find this in your simulation basis manager, right? After you have added the reaction set and you specify kinetic, this is where you, the software takes you to, right? So that you can actually make your specifications, right? So we will be exploring some of these sections, right? We'll be exploring some of these sections. Okay, so the first is rate basis. Let me see. Okay, so rate basis. Now, rate basis can be divided into two. Now, rate basis is basically the basis of that rate, that rate expression, right? Or the basis of the rate of that chemical reaction, right? So basically in Aspen, you have two types of rate basis, right? You have the reactor volume. So your rate can be based on reactor volume, or it can be based on catalyst weight, right? So, and yes, most of the time when you are getting or extracting kinetic data from research papers, they would either be in terms of reactor volume or catalyst weight, right? So that was why I gave that rule initially. I said you have to take note of the following. You have to take note of the rate unit and the concentration basis, right? So the rate unit is based on the rate basis, right? So these are very important things you have to look out for when you are actually sourcing your kinetic data, right? So it's either based on the reactor volume or the catalyst weight, right? So now, so you can actually determine the rate basis using the rate unit of the rate of reaction, right? Now, one thing to note is that, Aspen Hysys only gives, the option of specifying rate basis in terms of reactor volume, right? Right. So in terms of reactor volume, and yes, let me see. Okay. So you have the basis units. So you see the basis unit is in kg mole per meter cube, right? Right. So we'll be exploring this in the modeling. You will see the other units that are actually in this drop down, and you will see that all of them are based on volume, right? So they are based on reactor volume. Yeah. So when you are extracting data for your modeling in Aspen Plus, you have to keep that in mind, that you cannot use, you probably cannot use catalyst weight to specify your kinetics. So you have to source for kinetics of that particular reaction that is in terms of reactor volume, right? So you have to source for kinetics that is in terms of reactor volume for that particular process, right? So that is for your rate basis. Then you have concentration basis as well, right? So you know, in the rate expression, you have the rate constant multiplied by concentration, right? So, and for concentration, we have different kinds of concentration basis. So you have the mass concentration, you have the molar concentration, you have fugacity, you have partial pressure, you have activity, and then either mass or molar fractions, right? So you can also determine which concentration basis your rate expression is based on from the rate unit as well, right? So the rate unit can also give you information as regards which concentration basis you are making use of, right? So basically that's it. Then we also have the forward order and reverse order. Basically that is the order of the reactants, right? So you have a section where you specify the order of the reactants, right? The order of the reactants, right? So for example, in this in this one, so the reactant here is C3H6O, which is one of the reactants, right? And the order of this reactant is this value up here, right? Which is 2, right? So the order of C3H6O in this particular rate expression is 2, right? So that is what is supposed to be specified in that section, in this section, right? So in the forward order, you are specifying the order of the reactants taking place in the forward reaction, and in the reverse order, you are specifying the order of the reactants taking place in the reverse reaction. So that is how this works, right? So what do we have next? Let's see. Okay, so forward and reverse order. So yes, we have the general procedure for specifying kinetic reaction models, right? So the general procedure. So the first procedure is to choose the kinetic model after creating a reaction set. So first you create your reaction set, then you choose your model which is kinetic. Then you also have to make sure that the data bank source is the same as that was used while selecting the components, right, in your component list, right? So if you used Hysys data banks, you also use Hysys data banks here. Then if you used Aspen properties database, you also have to use Aspen properties database as well. Then also you specify the reaction components and their stoichiometry, right? Then you specify the basis, the base and the rate units, right? Then you specify the values of the different kinetic parameters, the pre-exponential factor, activation energy and the rest. Then you attach a reaction to the fluid package, right? You attach the reaction to the fluid package after it has been fully specified, right? So basically this is all that you are expected to do, right? So those procedures are what you actually follow when you are specifying this environment, right? This kinetic environment. So before we go into the example, so this is where the modeling starts. But before we go into this example, I want to show you two papers. Now, from this first paper, we have some kinetics. We have some kinetics here, as you can see. So now you see we have some equations on towards the left, and then we have the kinetics towards the right. Now from this table you see that this is actually a journal, right? So maybe I'll scroll up for you to see the name of the journal. So you have rate law. Now rate law is given in k mole per m cube s, right? So from this rate law unit, you automatically have an idea that this rate law is in terms of reactor or reaction volume, right? Yeah, reactor volume, right? Because it has k mole per m cube, right? M cube stands for volume, right? So from this rate law formula, you have an idea that these rate expressions are based on reactor volume. So when you are modeling your process, you are using the basis as reactor volume, not catalyst weight, right? So this particular table was actually well specified, right? Because some of them may not actually tell you the rate law unit, right? But this particular journal specified it, so it's easy for you to know that okay, this is actually based on reactor volume. Now in this okay, let's see this first rate expression. We have for the concentration of the reactant, we have P here, right? As you can see, let me zoom in. Is it possible? Okay, so I have zoomed in more, right? Yeah, so we have P here for this first one, and then for the second one and the third one we have C, right? So P stands for the partial pressure, right? So this is actually the concentration basis, right? So from the rate expression you get the concentration basis, while from the rate unit you get the rate basis, right? So this one, the rate basis is reactor volume, the concentration basis is partial pressure, right? Because you have P here, so P stands for partial pressure. Here you have C, so I guess this one, the concentration is the concentration basis is molar concentration, right? For the ones where you have C, the concentration basis is molar concentration, while for the one where you have P, you have the partial pressure. So you have a lot of concentration basis, as I earlier listed. You have fugacity, activity, and the other ones, mole fraction, mass fraction, right? So but these ones that are here in this particular journal are as regards partial pressure and molar concentration, right? So, and this rate law is based on reactor volume, right? So you can see it from here. Now, okay, let me show you the name of the journal before I leave this environment. Let me just show you the name in case you want to check the journal out. Okay, it's upside down, yes. So this is the name of the journal. So in case you want to check it out, by Abdulawid, right? detailed modeling of biomass gasification in a dual fluidized bed reactors under Aspen Plus. So, but what brought me here was the kinetics actually. That's what brought me to this particular paper. So, another paper we have here, right? This is another paper. Now, in this case, the kinetics is based on catalyst rate, right? And how do you determine that, right? How do you know it's based on catalyst rate? It is still based on the rate unit, right? So the rate unit determines what the rate basis is, right? So from here you can see k mole per kg cat, right? Kg cat, right? In this other one, what we had was k mole per m cube, right? In this one it was k mole per m cube, but in this one it is k mole per kg cat. That is weight of catalyst, kg cat. Do you get? Kg cat seconds, right? This one was kg mole per meter cube seconds, while this one is k mole per kg cat seconds. So you know that this has to do with the weight of the catalyst, right? So these are things you check out for when you are sourcing for your kinetic data, right? So basically, I think we have gone through the introduction, and now you have a solid foundation as to modeling kinetics, right, in Aspen Hysys. Before we go into the example, let me show you the name of the other, this particular journal as well, right? So before we just yes, so this is it. Techno-economic analysis for hydrogen and carbon production via catalytic pyrolysis of methane, right? Via catalytic pyrolysis of methane by Jared Riley et al, right? So this is the journal, so you can search for it if you want. It's in the International Journal of Hydrogen Energy, right? Science Direct. So you can search for it. So I think we can go into the illustration now, right? So this is now the part where we actually model kinetics. Yeah. So we have this particular process and we want to model it, and this is actually the rate of the reaction, right? So you have R is equal to K into CaCb minus CrCs over Ke, right? So Ke is the equilibrium constant, like I earlier said, that's Bk, right? So we'll be using that to determine the K prime or Kb, right, which is the rate constant of the backward reaction, right? So basically this is the data we have, right? So we have our rate basis as volume, so we have all of these, and then yeah, so the first thing is to identify certain things before we start the modeling. So from the reaction equation and rate equation, right, if you compare two of them, you have A would be ethanol, B will be acetic acid, R will be ethyl acetate, and S is water, right? So why that is said is because this is the reaction equation, right? So you have you have ethanol plus acetic acid to give you ethyl acetate and water, right? And this is a reversible process, yes. So now you have CaCb, CrCs. So A will be A is acetic acid, yes. Let me see. Okay. So A, I took A as ethanol, okay. So B is acetic acid, then I think R is ethyl acetate, yes, and S is water, right? So just to identify what we have here, then moving down, yes. So the next thing is to compare, the rate equation, with the yeah, to compare the rate equation with equation 11. So this is equation 11. I just copied it and brought it down here. So we are comparing this with the rate equation from the question, which is this right here. So you have R is equal to KCACB minus K over KCRCS, right? So this is just you expanding the rate expression, right? So you just expand this, so it becomes KCACB minus K over KECRCS, right? So just to open the brackets, that was what was done here, right? So just open the bracket and you will get this, right? But we already know that K over KE is K prime, right? So if you do your substitution, you should have something like this. You should have R is equal to K CACB minus K prime CRCS, right? So comparing this with equation 11, you can generate all of this data, right? So if you compare this with equation 11, you have that A will be equal to 1.26206 times 10 raised to power 6, which was given in the question. Then M, N, I, J, they are all 1, right? They are all 1 because you have CA. CA is also CA raised to power 1. CB is also CB raised to power 1. CR is also CR raised to power 1. And CS is also CS raised to power 1, right? So M is 1, N is 1, right? I is 1, and then J is also 1, right? So we are comparing this with this right here, right? So we are comparing this with this. So M, N, I, J are all 1. Then K prime is K over KE, right? K over KE. K over KE gives you 1.206 times 10 raised to power 6 divided by 1.5, right? So 1.5 is in the question, right? So you have K as this, right? 1.206 times 10 raised to power 6, right? You have this. Then you now have KE, right? Your KE is 1.5, right? So all you need to do is just divide this by 1.5, right? This divided by 1.5, and you should get this as your value, 804,000. Now if you substitute this back to equation 11 for better understanding, if you substitute the values here, if you substitute it back into equation 11, you will have this as your rate expression, right? So this is equal to what we had in the beginning, which is this, right? Just that we have substituted all the values where necessary, right? So we have expanded and we have done the substitutions, and then you generate a very detailed rate expression, right? So you can compare this, right? You can look at this and compare it with the initial rate expression to be sure that you understand what was done. So you compare this with what I have here, right? And be sure you are on the same page, right? So this is the detailed rate expression, and this now is what you can actually input in the software, right? So this rate expression is what we are going to be specifying in the software. So we are now ready to go into the simulation environment, right? Yes. So the first thing to do is to add the components. So in this case, I want to make use of the Aspen properties database. Yes, I want to make use of the Aspen properties database, right? Yeah. So we have ethanol plus acetic acid, right? Yes. Okay. So acetic, then we have ethyl acetate. Let me see. Yes, and then we have water. Yeah, water. So basically this is what we have. Then now to the fluid package. So we use the Aspen properties data banks here. So we are still going to make use of it in the fluid package. So you click on Aspen properties. Yeah, so Aspen properties to choose the fluid package. So from the question, the fluid package is NRTLHOC. Let me see. Yeah, fluid package is NRTLHOC. So we search for NRTLHOC. You can use all. All helps you to search for all the fluid packages present in the Aspen database. So NRTLHOC, okay, so we have it here. So you just click on it and then it is specified. Yeah, so NRTLHOC. So we have specified the components fluid package. So the next is reactions, right? So you click on add. Right? So in add, you click on add reaction, right? So now, like I said, you must ensure your reactant source is the same as that you use to select your components, right? That is the first instruction for specifying your reaction accurately, right? So you ensure that it's from the same source. So we used Aspen properties in the component list and in the fluid package. So we are still going to use it here. So you click on Aspen properties. If you used Hysys data banks, you click on Hysys data banks. So you click on whichever you used, right? Now, so clicking on this, you click on kinetics because it's kinetic that we are using for this model. So you click on kinetic and you click add reaction. Add reaction, right? So now yes, so we can open this reaction window and then it brings us here, right? So this was what I showed you in the introduction, the kinetic environment. So we add our then we have yeah, acetic acid and this. So second is to specify your stoichiometric coefficients, right? So negative for reactants, negative sign for reactants, positive for products. Like I said in previous reaction tutorials, your balance error, you ensure is 0 and then you move on, right? So the order for each of the reactants, right, you can get it from the final equation I generated, which is this, right? So it's easy now. With this equation, it's very easy. So for the forward reaction, we have A, B, 1, 1, right? So 1 is the forward order for reactant A, and 1 is the forward order for reactant B, right? For reactant B. So it's just to input these values, which is 1, 1, into that section. So it's already there, right? So this is like the default, right? But you are supposed to change it based on the rate expression, right? Because for the other example we had before, you see the rate expression, you see this one is 2, right? So you can't put 1 there. 1 cannot be there because it's 2 in the rate expression, right? So if you were working with this reaction, you specify 2 instead, right? So it's based on whatever you have in that section is based on the concentration basis, right, for that particular reactant. So that's what we are working with. But in this case, we have it as 1, right? So we have it as 1. So it's already inputted, right? So you have it forward order 1 1 for ethanol and acetic acid. Then for reverse order, your products are your reactants. For the reverse order, you still have the same process. So from the equation for reverse, you have your reactants, which are the products of the forward reaction. You have them as the order as 1 for the first reactant, and for the second reactant also 1. So that is still what is inputted here, right? So that's what's still inputted here, and then this is fully specified, right? So you have to take note of the reactants order from the rate expression, right? So coming over here, you have your basis. So for this case, base is molar concentration. Now, yes. So from the question, you have E is equal to 54,240 kg per kg mole, and Ke, which is the equilibrium constant, is 1.5, right, based on molarity, right? So based on this particular phrase here, I made the assumption that the basis is molar concentration, right? Molar concentration. So you have other bases, right? So these are actually the basis for the concentration, right? The concentration basis, yes. So because I listed all of these when I was doing the introduction. So you have molar concentration, mass concentration, the mole and mass fraction, activity and fugacity, right? So these are the concentration bases, the different concentration bases that you have, right? So the next is the base component. Base component is ethanol, yes. But in case you want to change your base component, you can decide to change it. But in this case, I want to use ethanol as the base component. Then reaction phase is liquid phase, yes. That is also in the question. Let me see. Yes, I think it is. Okay, yeah. So it says consider the ethyl acetate process in which ethanol reacts with acetic acid in the liquid phase to form ethyl acetate and water. So the reaction occurs in liquid phase, right? Then what else? You have the minimum and maximum temperature, right? So I think this is just the range for which reactions take place. So you have the lower bound, which is minus 273, and then you have the upper bound, which is 3000 degrees Celsius. So what this means is you may not really have reactions occurring below this temperature or above this temperature, right? So this is like the range in which most reactions occur, right? So you have minus 273 and then max 3000. But I guess you can still change it if you want to, if you feel like your process may occur above or below this. You can actually edit this and specify the temperature you want as the range, right? Then you have the basis unit and the rate unit. So this one, the rate unit is kg mole per meter cube second, right? This is similar to what we found in that research paper, right? If I'm not mistaken, yeah, this paper, right? So like I said Hysys is based on reactor volume, right? That is why you have meter cube right here. So, and all the other units there are associated with volume, as you can see. So you have liter, you have centimeter cube, you have milliliter, you have feet cube, you have feet cube. So basically that's it. So you see that all these units are associated with volume, right? So that is why I said Hysys, in Hysys you specify kinetics that are related to reactor volume, right? Then you have the basis unit, right? The basis unit. So this basis unit is associated with the concentration basis that has been specified here. So we specified molar concentration, right? And then you have kg mole, right? So now so if you specify let's say you specify partial pressure, you will see that the unit will change, right? So you see it changes to kPa, right? Or whatever pressure unit you are working with, right? So you can change your pressure unit, right? So this case occurs when your rate concentration is based on P, right? Where we saw P in that particular journal, right? So in that case, you'll be specifying any of these units, right? So, but in this case, we are making use of molar concentration. So I'm going to change it back. So this is what we have, right? So basically, all our basis has been properly specified. No, this is liquid phase, right? So this is liquid phase. So I think everything is properly specified here. So we can now specify the kinetic data that we have. So yes, going back to this, from our final expression, we have this. So 1.206, let me see, 1.206, 1.206 is 6. That is for A. 1.206 is 6. Then activation energy is 54,240, I think. Yes. So let's go back. 54,240, right? So you are specifying it without the negative sign. So 54,240. So I can copy this and paste it here. Yes. So in this case, we are specifying both the forward parameters and the reverse parameters, right? Because it's a reversible process. But in a case where we don't have a reverse reaction, all of this can be empty, right? So yes. So then we specify this as 804,000. Yes, right. So now from this we can leave B empty, right? Because from our rate expression we don't have any values that are associated with B, right? Raised to power TB, right? And I told you that in most cases B is usually 0, so you just have AE raised to power minus E over RT, right? So you can actually leave this empty. So we have fully specified this environment, right? Then we can now attach to fluid package. So attach to fluid package, just click on this and then you click on add and you are ready. So basically that's it. So we can now move over to the simulation. We can move over to the simulation environment to model the process. So this is our simulation environment. Now back to the question. It says model a CSTR and PFR whose temperatures and pressures are 50 degrees Celsius and 101 kilopascal respectively. Both ethanol and acetic acid streams have molar flows of 50 kg mole per hour. Pressure of 110 kilopascal and temperature of 20 degrees Celsius. Right? Then the volume of the reactor is 3 meter cube. It says determine the composition of the product stream. Right? So we are supposed to determine the composition of the product stream. Right? So yes. So we have been given all the details we need. So from your model palette, you can get reactors from the reactor section. So you have your plug flow reactor PFR here, and then you have your CSTR, which is the first CSTR, right? Continuous stirred tank reactor. So yes, so we are modeling both of them in this particular illustration. Yeah, so I want to make use of a mixer for the two feed, right? So I want to make use of a mixer for the feed streams. Yes, so I'm attaching my material streams. So we have ethanol, and then we have acetic acid. Yes, so yes, ethanol and acetic acid. So I can still replicate it here. Yep. So we have, I'll name this one ethanol 1 and acetic acid 1. Yes, so this is what we have. So we can specify their properties and composition, right? So yeah, let's enter. So for ethanol stream, we have a mole fraction of 1. Then we can specify the conditions. I think the condition is 50 kilomole per hour. Yeah, 50 kilomole per hour, pressure of 110 and 20 degrees Celsius. Okay, 20. Yeah, 20. Pressure of 110 and 50, I believe. Yes, so you have it fully specified. Let me just confirm. Pressure of 110 kilopascal and 20 degrees Celsius. Then 50 kg mole per hour. So yeah, this is fully specified. So I can easily copy this here. Yeah. So I can copy this. Let me see. Composition of ethanol is 1. Okay. Yeah. Composition of ethanol is 1. Then the conditions, I can copy, shift, copy this, and then paste it here. Yeah. So it's fully specified as well. So the ethanol stream is specified. I think they both share the same composition, ethanol and acetic acid. Yes, they share the same composition and conditions. So I can also do the same, right? So I can copy and paste. So I just paste here, then specify composition of acetic as 1. Enter. Okay. Yeah. Same procedure here. Paste. Enter. Right? And it's okay. So let me see. Yes. So we have this composition. Acetic is 1. Then we have this ethanol is 1. Yes. Okay. And then we have this acetic is 1. And then we have this ethanol is 1. Okay, so we have finished the first phase of this model. So at this point, we can begin to consider modeling the reactor. So first we can add, let's add streams to the reactor. Attach material streams as usual to your equipment. That's the first phase. Yes, so we can specify this. Then yeah, we can attach to this as well. Yes, then we can attach the inlet mix 1. So mix 1 is the inlet to this, and then mix is the inlet to the CSTR, right? So after attaching the inlets, the next thing it says is requires a reaction set, right? Requires a reaction set. But but before we go to the reaction set, the question said something. It says model a CSTR and PFR whose temperatures and pressures are this and this, right? So we have to find a way to also incorporate these two conditions, right? 50 degrees Celsius and then 101 kilopascal, right? So we have to find a way to actually incorporate this. Yes. Okay, so we want to drop the pressure to the pressure of the inlet is about 110, which is the pressure of the 2 feet. So we want the CSTR and the PFR to operate at 101, right? 101 kPa. So what we can do is to specify pressure drop, right? So under design, you can find pressure drop in the parameter section, right? So I will specify pressure drop as 9 kPa, right? And why I'm doing that is because yes, the pressure is 110 and then the CSTR is supposed to operate at 101, right? So 110 minus 101 is 9, right? So if you subtract, you should get 9, I believe, right? I believe you should get 9. So that is why I'm specifying 9 kPa as the pressure drop. Then also so that's for the pressure. Then for the temperature, we can actually control the temperature by adding an energy stream. I already told you that in the last tutorial when we did our conversion and equilibrium reaction models, right? I told you about how to maintain a particular temperature in a reactor. So we are going to be using that knowledge here as well. So our feed is at 20 degrees, but we want the reactors to operate at 50 degrees Celsius. So we can add an energy stream here, right? So we add an energy stream. Then we can now add a reaction set. It says requires a reaction set. So we go to reactions tab, and you select your reaction set 1, right? Set 1, all right. So after specifying your reaction set, it now says volume not specified, right? So for your volume, you can specify it in the ratings tab. Yes, in the ratings tab. So the volume was given in the problem as 3 meter cube. So we can easily input that here. So we have 3 meter cube here. Yeah, so 3 meter cube, and we are almost done with this particular reactor. So the last thing is the duty, of which we can solve that by specifying the outlet temperature. So the outlet temperature, we are working with the 50 degrees Celsius of the reactor. Yeah, 50 degrees. So I will just specify 50 degrees here, right? So once I specify 50 degrees, the reactor is fully specified, right? The reactor is fully specified. So we probably follow the same procedure for our plug flow reactor, right? We can follow the same procedure for it. Yes. So following the same procedure, says requires a reaction set. Okay, let's add our energy stream. So Q1. So we have added an energy stream. Then let's see. Okay, we can specify the pressure drop as well, right? So we specify pressure drop in the other reactor as 9 kilopascal. So we are doing same here. Yeah, 9 kPa. User specified 9 kPa. Then we can now add a reaction set. Reaction set is set 1. Yes. So after adding reaction set, it says unknown dimensions. So that has to do with the sizing of the reactor. So you can specify volume. Volume is 3 meter cube. Yes, 3 meter cube. So 3 meter cube, it still says unknown dimensions. So for plug flow reactor, you have to take note. For plug flow reactor, you have to specify either the length or the diameter, right? So the volume is not sufficient in this case, though it's sufficient in the CSTR, right? So in CSTR we specified only the volume, but in plug flow you have to specify either the diameter or the length, right? So plug flow reactors work with length. So in this case I want to just copy this, I'll copy this calculated diameter here. So I want both of them to operate at the same conditions. So I'm actually copying that diameter and I'm pasting it here, right? So diameter is paste. Diameter is 1.366. Let me confirm. Yes, diameter is 1.366. So I just copy that and we are good, right? So the last thing is to now specify the temperature which solves the duty, right? So the temperature is is 50 degrees. It's 50 degrees, right? So basically this has been modeled, right? So the question said we should find the compositions. We should find the compositions of the product, the reactor product. So that is what we'll be looking at right now. So before we check the composition and then other things from this our model, I would like to make a quick correction. So back to back to the rate equation. Now when you divide this by this, you get 804,000, right? So this is actually a mistake right here, right? So it's supposed to be 804,000, which is this, not 80,400, right? So 804,000. So this must have been an oversight from me, right? While typing this particular this. So you have to add another 0 to this so that it becomes 804,000, right? So K prime or K for the backward reaction is 804,000, which is correct right here, right? But it's wrong here, so just add one more 0 and also do that in your properties environment. So just go back to your properties environment if you are following the procedure and make your adjustments, right? So 804,000, which is 8.04 times 10 raised to power 5, right? So that is what should be here. So please take note of these adjustments before continuing your model. Kindly take note of this, right? So that's it. So we can now check our results. Yes, I believe we can check our results. So from this we have this is the composition, right? So this is the composition of the liquid and the vapor. And then that is for the CSTR. Then for the plug flow, we have this. So I guess we can open both cases together, both forms. So this is for PFR. So you can see the composition here. So this is the composition. So you have the composition of the products, which is ethyl acetate and water. Then for the CSTR, we also have the composition of the products, which is 0.265 for ethyl acetate and water. Right now, you will notice something from the CSTR, right? So CSTR has two outlets, right? The CSTR has two outlets. You have the vapor outlet and the liquid outlet, right? So go back to conditions. You will see that the vapor outlet has a molar flow of 0. So what it automatically means is that nothing is coming out from the vapor outlet, right? And that is how it's supposed to be, because this particular process is in liquid phase, right? You remember we specified liquid phase. So this process is in liquid phase. So nothing is supposed to come out from the vapor outlet. That is why you have the vapor at 0. So our product from this reactor is coming out from the liquid stream, right? The product from this CSTR is actually what we have here, right? In the liquid stream, not what we have in the vapor. So you forget about this composition of vapor, because by the time you multiply this by 0, you still get 0, right? So this is what we are working with here, right? So you have your conditions for the liquid. So the liquid is where you have something coming out, right? So this is what we are working with. So that is the first comparison. So we have I believe more products were formed in the PFR, because the composition of the PFR has 0.2753, right, for both products, while for the CSTR we have 0.265, meaning that the CSTR produces less amount of product. And you can also confirm that from the reaction section. So you have the conversion. So you can determine conversion for your kinetic models, right? That is one of the advantages of modeling kinetics, right? So you specify your kinetics and the software calculates conversion, right? It calculates conversion. So conversion of ethanol is 53.01, while here conversion is, let's check. See, conversion is 55.05, right? So you see that the conversion of the PFR is slightly higher than CSTR, and that is why you have more products coming out from the PFR, right? So more of the reactants are converted to products, right? And you can confirm that via the conversion, right? So you can see the composition of the products, right? So we can see that from the worksheet. Just click on composition, and this is actually the solution to this particular problem, right? So we can actually make some of the data visible, right? So you click on show table. So this is the condition of the products, right? Show table. Just click on show table and you get this table out. So I want to add more things to the table actually. So I will just I'll just move this forward. Yes, so and move this, sorry, and just move this downward. Sorry about that. Yes, so let me see. Okay, let me bring this up a little. Okay, I think it's okay like this. So I want to add more details to this, so I just click add variable, and then so I want to add the molar flow of all the components in the product stream, right? So I just go to master components molar flow. I click on the drop down, and then I come down to it, master component molar flow. Let me see. Yes, master component molar flow, the drop down, then I select all of them, right? So I select all of them, and then I click OK, right? So it gives me this information. So I'll do likewise for the PFR as well, right? So master component molar flow gives you the molar flow of each of the individual components in that particular stream, right? Master component molar flow, not mass flow. But if you want mass flow, you can also choose mass flow. So I'm using molar flow for this illustration. Yes, so I just add all of this, so all of them appear at the same time, right? So you have that, and I can exit this. So this is for CSTR, and then this is for PFR, right? So basically this is what they're asking for. You can also add your molar fractions of each of these components to this table if you like, right? But I don't want to do that so that the table does not become too long, right? So, but basically this is what was requested for in that particular problem. So this is how you actually model kinetics in Aspen Hysys, right? So this is actually a first video. More videos will be coming up as regards kinetics, because this is not the end of kinetics. So we will still have a couple of videos on it before we move on to a new topic. At this point, we have come to the end of this particular tutorial. If you have questions, let me know in the comment section. Like this video, share with your friends, and then subscribe to this channel if you have not done so yet. Thank you for joining me in this particular tutorial. Do have a good day.